Okay, good morning to everybody and welcome to our Severo Ochoa IAA colloquia. Today we are very happy to have with us Dr. Cherry NG. She started the position as permanent astronomer at the Centre National de Recherche Scientifique in France in the last year. And she moved there to France from her research associate position at the Dunlap Institute for Astronomy and Astrophysics in Canada. It was held jointly at the SETI Institute and the UC Berkeley SETI Research Center in the US. In fact, while we were talking before doing this presentation, we got to know that she was working here in Spain in the year 2009. She was working in ISAC, close to Madrid, where she was working at that time for Examen Newton. Then she knows our country. Although, and she said that it's too cold just now in Granada, but we are quite happy to have the rain and some cold weather during these days. Okay, the Dr. Ng's research interests are in the areas of pulsars and pulsar polarimetry, in the area of fast radio bursts, neutron star binaries, algorithms for finding pulsars, including detecting new ones, Faraday rotation measures of pulsars, including also just now SETI, as we will notice during her presentation. In fact, she has been doing multi-wavelength work in the last years, ranging from radio to X-ray. She did her PhD studies at the Max Planck Institute for Radioastronomy in Bonn, Germany. During this period, she discovered more than 100 rapidly spinning neutron stars with the Australian Parkes telescopes. That is one of the SKA pathfinders. Then she moved to Canada, where she has been working with the Canadian Chimie telescope. This is another SKO finder, but I would say a very productive one, developing an algorithm that has detected more than 1,000 new FRBs. In fact, she was telling me just before that more than 5,000 FRBs have been discovered already by Chimie. That is really amazing. In fact, she developed an algorithm that that was using big data outputs of the order of 13 terabytes per second while they're with Chimie. This developed into hunting for technosignatures in the area of search for extraterrestrial intelligence, SETI. And in fact, just now she is the leader of the project scientist for the MeerKAT and the Very Large Array SETI searches. This is without any doubt a very fantastic project. She is just now also one of the two co-chairs in the Cradle of Life SKA Science Working Group. In fact, this is the SKA Science Working Group with the most Spanish members. There are more than 17 Spanish members in this group. And she's also a member of the External Advisory Committee of SKA, where both of us are sharing our pertinence to this committee. In fact, we have seen also her in the media recently due to her work on using artificial intelligence and also machine learning to find SETI candidate signatures in radio data. Okay, today she will talk to us about a new digitized age of SETI, interferometric, commensal observations, and machine learning. Welcome to our institute, Cherry, and the floor is yours.
Hey, thank you so much for this introduction. Testing if it's working. Cool. Yes, meeting is recorded. So yeah, today we'd like to talk to you about interferometric SETI projects using the MeerKAT and the Very Large Array, the VLA telescopes. And these are in partnership with the Berkeley Institute and the SETI Institute. So, go to the next slide. Well, so in the last decade, the Kepler mission has discovered thousands of exoplanets. And it is now known that probably 1 in 5 stars have exoplanets that are within the so-called habitable zone where water can exist in liquid form. That is to say, all in all, there could be billions of Earth-like planets out there. The search for the origin of life has never been so relevant. And this is not a surprise that cradle of life as you see here, is one of the 14 key science goals of the square kilometer array that is supposed to be the most sensitive radio telescope ever built. Now, the SKA, Cradle of Life Science Working Group, has a total of 139 members. And this is a breakdown of the membership. And you can see by country, it is quite even. There is not one single country that dominates, which is good. And in fact, Spain is one of the largest representation here, well, the second largest, with 13% of the members. And if we look a bit closer in the Spanish scientists, well, most of them come from the ICE, but the IA is really not far, a close second, accounting for a quarter of all these Cradle of Life members. So I am definitely in the right place, talking to people that are already interested in this topic. Now, what exactly is inside Cradle of Life? It's a really, really broad science working group. We say it's a mixed bag because so many things can help us to understand the origin of life. One primary example is the study of planet formation. In recent years, the ALMA telescope, for example, has provided stunning images showing the protoplanetary disk and the fact that there are these concentric dust rings and gaps, which are the initial condition for planet formation. So this sounds quite good. Actually, I'll move this a little bit. Send my way. So this sounds quite good. But in fact, there are a lot of things we still don't exactly know how these planets are formed. For example, we realize that the time it takes, the lifetime of this protoplanetary disk, it's rather short compared to the time it takes to collect enough material to form planets at large radii. There's also the so-called centimeter barrier problem. The thing is, we have observed millimeter size particles from ALMA, for example, in these rings, we have seen millimeter size particles. But how do these little particles get together to form centimeter size pebbles and then form rocky planets? That's not clear because from laboratory experiment, we see that these tiny little particles, if you try to put them together, they will actually most likely fragmentation into small pieces, or perhaps they will rebound. It is very hard to make them stick together. And also these particles in the disk, because of the solar wind, they will experience this aerodynamic drag that actually pulls them towards the star in the center. Before that, they can actually grow big enough to form planets. So we don't really know. That's the bottom line. Now, the SKA meet with the band 5 receiver will be really the first time that we have a sensitive enough instrument at the right frequency range to observe the centimeter size pebbles, because we want to know exactly whereabout in the protoplanetary disk they are and at which stage they are formed to help piece together this puzzle. Next. Another strong interest in the Cradle of Life group is the detection of prebiotic molecules. It's a type of biosignature. Now, amino acid in particular is of great interest because, as we know, they can help to synthesize protein in living organisms. And we have already detected amino acids in the in meteorites and comets. So we believe we should find some in the interstellar medium, but we haven't found any. It is really hard because they're weak and it's too we just don't have enough signal to noise. Now, it has been proposed that maybe in this protoplanetary disk, in the molecular clouds, there are some regions that are colder. This what's so-called the ice. There are some colder parts where these amino acids can be protected from the interstellar radiation, so that maybe they could actually form these molecules, or perhaps in the prestellar cores that are also relatively cold regions. Now, with the SKA made once again, we have high frequency to probe this cold region to hope to make the first detection of amino acid in the interstellar medium. Another one I want to mention is the magnetic field of exoplanets. Studying magnetic field can help us really understand the planetary interior and the dynamo process. And in fact, that's how we realize that our Earth has a liquid core. There's no other way to, probe inside. The study of magnetosphere can also tell us whether these exoplanets are protected from the solar wind, because it will have implications for the habitability. This is why we are interested to study magnetic field of exoplanets. And in fact, our own Jupiter is extremely bright in the decametric frequency range. So we might expect that exoplanets, if they are like our Jupiter, they would also be bright. And in fact, as we know, there are a lot of hot Jupiters that are much closer to their sun, which means they will have a stronger interaction with their sun, and that can drive an even higher magnetic field. And so this is something that people are really interested to detect, although so far it hasn't happened yet. Once again, SKA, but now with low, because we need a lower frequency range, might be able to give this first discovery. Now, there's so much more in Cradle of Life. I just won't have time to mention. And the fact is that there are these experts at the IAA that know so much about them. So I won't be able to explain their science better than them. So I'll let them do the job. And today, let's go back to SETI, which is one of the main interests in Cradle of Life. And let's talk about what SETI is all about, how do we do it, and what have we done so far? Okay, what I want to talk about here. So SETI is we are searching for technosignatures, which are signals generated by advanced civilization from outside of the Earth. And this is kind of similar to the biosignature domain, where they look for molecular lines, maybe water or some signs of life. And we SETI, we look for the technological signature. Now, we don't know exactly what to look for. Obviously, we haven't detected anything, but we can make some guess. For example, we can see how human technology looks like from space. And this is what is shown here. This is the Voyager spacecraft detected by the Green Bank Radio Telescope in the US. And you can see it's and this is a time versus frequency data. And you can see that the Voyager is very narrow in frequency, and it's kind of drifting. So we think this is how a technosignature could look like. And the reason is that we think it would be a narrow in frequency range, because human technology, we have been using filters to concentrate information in a very small spectrum for decades now. For example, in the car, we change a bit the frequency, we listen to another radio station. And this is an example of how we concentrate the information, store different things. So maybe another civilization could do the same. And so then the other thing is, the narrowband. So the filter, this is good. It is also useful because we can easily distinguish from natural astrophysical signals, which tend to be much broader in terms of wave bandwidth. So here we're talking about like hertz width, whereas astrophysical signals typically hundreds of megahertz at least, or megahertz at least. So it's then if we detect something so narrow, we can be sure that it's not astrophysical. This is, it's helpful this way. And why is it drifting? We think it would be this way because if there is something coming from an exoplanet, for example, and this is Earth, and now because of the relative acceleration between the exoplanet and the Earth, we would see this kind of Doppler effect. So if the signal would be drifting in time and frequency. Compared to a signal that is from Earth, it would more look like a vertical line because it doesn't drift with respect to the Earth, in principle. And now, where do we go look for SETI signal? Like I mentioned in the beginning of the talk, using MeerKAT and the VLA, now these are radio telescopes. And why do we want to use radio telescopes? We think radio might be the way to do it because radio is relatively cheap to produce, well, telecommunication in radio. And this is what we do on Earth. So maybe other civilization would do that. And also, as you see from this figure, the radio band is transparent through the atmosphere, so we can detect from ground base, which is cheaper than going to space. Now, SETI search involves a massive parameter space. We already talked about this drift rate because of the differential acceleration between the exoplanet and us, but we don't know that a priori, so we need to search for many different slope of the drift. And then there's also the frequency range. We said, okay, let's try radio, but radio is still quite broad. So where exactly? Some people say, well, maybe the water hole, which is like at 1.5 gigahertz, because there's relatively fewer astrophysical signals or background noise from this range, but still, we don't know, right? Not necessarily from there. And then there's the sky coverage. It is estimated that there could be 400 billion stars in the Milky Way galaxy. So there's a lot of stars to search and time domain. Now, the signals could be intermittent. Let's say we looked at some stars, we didn't find ETI signals, but it doesn't mean there's nothing. It could be that it wasn't emitting at this particular time. So that means maybe we have to search again and again. And then finally, telescope sensitivity, how far we can detect the signal. And in the field, people have typically used the archival planetary radar as standard. Now, this telescope is no longer functional, but it used to be the most powerful planetary radar on Earth with 10 to the power 13 watts. So we typically like to say, how far can we detect the archival if it was somewhere else? And that let us compare the sensitivity of a given search. Anyway, a lot to think about, and it's an expensive project. And this is where Breakthrough Listen comes into play. Breakthrough Listen is a 10-year, $100 million project to support the search of SETI. It was originally administered through the Berkeley SETI Research Center in California, but just last year, Breakthrough has moved its headquarters to Oxford in the UK, partly also to get a closer relationship with the SKA because we are very interested to use the SKA. Now, Breakthrough Listen, the mandate is to study 100 galaxies, to analyze the galactic plane, and to monitor 1 million nearby stars. And our work has spiked renewed interest in the community. And a few years ago, we detected this BLC1 signal. Well, in the end, turns out to be RFI, but the process was really interesting that our analysis made the cover page of Nature Astronomy. So that was pretty encouraging. Now, one bottleneck of the search of SETI project has been the slow mapping speed. Like we said, there's so many stars and we just can't cover them all. From the beginning, Breakthrough Listen have been using the Green Bank radio telescope in the US, 105 meter, and the Parkes radio telescope in Australia. So these are two of the biggest single dish radio telescope we have available, and Breakthrough Listen, we're purchasing time on this telescope about 10-20% of the time to search for SETI. And we observed of the order of 1,000 stars and generated 2 petabytes of data, and it's all publicly available. You can download it here. So if you want to go search, you're welcome. And in fact, you can even use the data for something else. You don't have to search for SETI. It is just public data. So that's great. But 1,000 stars is not much compared to all the stars of the Milky Way galaxy. And so we are now commissioning interferometric SETI instead, and that's the topic of today's talk. Now let's look at the interferometric telescopes that we have. We are using one is MeerKAT, as I guess we all know about MeerKAT. It's a telescope in South Africa, 64 dishes. One of the best instruments we have now, and it will in fact become part of the SKA within the next few years. And we also do a search with the VLA in the US, and it is kind of like the sister survey in the Northern Hemisphere. We also work with the Allen Telescope Array, the ATA, which is managed by the SETI Institute. The telescope is in California. Now, this telescope is almost exclusively used for the study of SETI. And so it's really useful to have it because we can develop the software using ATA and then apply to MeerKAT and the VLA. But I haven't explained exactly why interferometers are better. And this is because we can map more sky thanks to the fact that they have, in fact, smaller antenna. Smaller antenna means that they see more sky, larger field of view. The instantaneous field of view is larger. And in this cartoon, I am representing somebody, a primary observer, using MeerKAT to look at a pulsar. But in fact, MeerKAT can see a lot more than just that one pulsar. It has a larger instantaneous field of view represented by the green cone. So what we could actually do is to form these so-called commensal beams, the blue ones. We can point the telescope using software to study different locations all within the green area. And we can in fact be monitoring multiple stars at the same time, looking for SETI signals. In addition, both of these telescopes, MeerKAT and VLA, they have this so-called multicast Ethernet architecture. That means that we could kind of make a copy of the data simultaneously as other people doing some other research, like other primary observers, 24/7. We can be using the telescope to search for SETI. And I think this is a way to go because, well, okay, SETI is interesting, but maybe we're not finding anytime soon something. So if we can piggyback on something else, this is a great use of resources. And so here is a plot to demonstrate the commensal search capability. Plotted here is the stars that we have observed with Breakfast and Green Bank, the green dots, and the Parks as the red dots. And on the right is a count of the unique number of stars observed versus time, and the same color coding. So like I said, about 1,000, of the order of 1,000 stars have been observed using these two telescopes. Now, with the MeerKAT and the VLA coming online, we will be observing so many more stars thanks to the capability of this commensal observation, this multi-beaming thing that we can be recording 24/7 instead of purchasing 10% time, which is costing a lot and still not much. Now, you see with the MeerKAT, the blue, we will be observing 1 billion stars in just about 2 years, I think. And the VLA would be even faster. And that is because the VLA has a sky scanning program, a primary observing program called the VLASS. And this VLASS program is just supposed to scan the whole sky bit by bit. So this is best. This is great for us because we just want to scan the sky, really. We don't. Okay, but the sensitivity is a bit less. So it gives us a lot of stars, but not as sensitively. That's that. Okay, here is a plot, a figure of merit of SETI programs that have been conducted. It was made by one of my previous students, Leo Risk. And so what he did was that he looked at all the SETI programs that have been conducted. He compared their sky coverage, like how much sky each project studied, and the observing frequency, which window in the electromagnetic spectrum. And then he color-coded them in 3 levels. So low sensitivity of blue ones means we can detect irreversible if it was 5 parsec away. Yellow is mid-sensitivity, irreversible 25 parsec away. Or red is the high sensitivity, detecting irreversible 75 parsec away. So that's what we have. And if we look at a bit closer, some of the first SETI programs were done sort of in the 70s, 80s. So they were state of the art at the time. But if we look in this plot, you see that they occupy such a narrow range of the frequency spectrum. It just looks like a line, but no, in fact, it's just a tiny region of the frequency spectrum, not that much sky and not very sensitive. Then comes breakthrough listening using green band and Parkes was already improving things a lot in all the 3 waves. And now with MeerKAT and VLA, it will be even better. The VLA is great because it also has a very large frequency range. So it probes some area that has never ever been searched for SETI, while MeerKAT is extremely sensitive. That means we have we can probe the largest distance. Okay, what now? Then we have also been using trying to incorporate machine learning in the SETI search. So this is a image trying to explain how we typically, in the past at least, been doing SETI observations. What we do was this so-called cadence observing. We would choose a star and we look at it and imagine there was a SETI signal. We see some narrow band drifting thing in this star, which on scan we call, and then we look somewhere else, a totally different part of the sky, which is the off scan, and we should see nothing. And then we would look back to the chosen star, and we should see it drifting accordingly, look away, look back. So we do that like 6 times like this to be really sure that, to make it more robust, let's say. We still can't be 100% sure. We make it more robust that even if we detect something, we should see it like 3 times in the right scans. This is how we were hoping to detect SETI when we were observing with the single dish telescope, when we were buying times, because basically the telescope was just for us. So we pointed here, we pointed there. This is what we did. So with my student, Peter, we were developing a machine learning algorithm. This is a thing called the variational autoencoder. It is a machine learning model that is really good to how to say, compress data and make it more simple. So this is a schematic of the algorithm. It's so complicated. In fact, it's not that complicated. What it has is just an encoder. Yeah, so it's an encoder, and then it's reduce the dimension of the data. We pass it training data to this encoder model that we develop. And it reduced the dimension of the data to a bottleneck, and then it flips the encoder around. It's exactly the same, just reverse kind of. Then it's the decoder, because what we're trying to do is to reproduce the training data. So if this process managed to reproduce exactly the training data, then we believe that the encoder model is created properly, and then we can transfer this weight, the encoder part, to the actual data that we want to search, passing through the encoder, and then we have a random forest classifier. So this way we can compress the data completely in an unsupervised way, and this is in fact why we chose this variational autoencoder, because it's unsupervised. So we were hoping that it will find us some signals even that we didn't teach it. We didn't say, maybe SETI doesn't, because we said we actually don't 100% know that SETI has to be like this. So maybe this program will find other types of weirdness in the data that could be SETI or not. The other good thing, as I mentioned, is that it can reduce the dimensionality. It is disentangled, so the nodes are learning the features separately. So it's very good at extracting feature in an unsupervised way. Yeah, so this was quite successful. We found a bunch of signals that look pretty much like what we said we would want to look. So have we found SETI? I don't think so. We tried to reobserve these positions with the green band again to confirm, and we never saw the same thing again. So I think even though it looks like it, yeah, but I think without confirmation, we just can't prove it. So that's that. But I think this work was really still very interesting because what we have demonstrated is the potential of using machine learning to help in SETI because it was able to find something. Oh yeah, I forgot to mention because this was archival data. It has already been searched for SETI. But they didn't even find these signals, so that we, I think, honestly, are right. But they didn't even find this when we went back to compare, and they didn't detect it. So the machine learning model really has some advantage here that we hope to explore more. And this is what Peter is now continuing doing with Daniel Check as one of our postdocs. And they are now trying to develop the model to the interferometric cases as well. Now, the thing is with MeerKAT and VLA, we don't control the telescope anymore. We can't point it on and off and do the cadence thing. But we can still try to make some spatial filtering using the multi-beamness, like the same animation that we've seen earlier. The idea would be that we analyze all the beams, and if there were RFI, let's say from mobile phone signals on the Earth, we probably see it in many or all of the beams, whereas if there were SETI signals, it was being only one beam. So that's what Peter and Daniel are trying to do. This is, for example, well, this is actually MeerKAT data that they collected. MeerKAT SETI forms these 64 beams, like so they were pointing them to different stars, and then they were trying to look, okay, once the signal was detected in one beam, and is it in the other beam? And yes, so okay, they found RFI. But this is work in progress, and yeah, no, it's looking pretty interesting. Putting these steps together, this is kind of a data flow of what we do. Like the data that's recorded, channelized by the FPGA. So these parts belong to the observatory, let's say, and then very high data rate coming through multicast Ethernet to a dedicated SETI GPU cluster. And in this cluster, then what we do is we further channelize the data because we need to detect these hertz with signals. It's really, really fine. We need to have this good frequency resolution. We do the beam forming, remove RFI, and then we search using machine learning or the Doppler technique. I have some photos here from the two sites. You can see this one is the our SETI GPU cluster at the Curry Desert for the MeerKAT project. It is all built out. We have 105 GPU nodes, and this is work led by Daniel and Dave from Berkeley. And on the VLA side, it's a project led by Chanoa, Jack, and Savine from the SETI Institute, and 24 servers have been installed. As you can see the photo here. They're currently observing with VLASS now, and we have successfully detected the Voyager signal from this SETI backend. So it's good. It shows that it is able to ingest the data and detect the Voyager signal. We are commissioning the last stage of the software pipeline. And finally, we are looking forward to using the next generation radio telescopes like the SKA and the NGVLA, because these two telescopes will be the only facilities so far to detect what we call leakages from omnidirectional ETI transmitters. Because so far, all the stuff that I talked about, we have to assume that the aliens are trying to communicate to us. They are sending us something, and it's only that we have the sensitivity to detect, because otherwise it's just too weak, the signal. Now with SK and NGVLA, we think they have the good enough sensitivity to detect leakages, which is just that they are like the TV signal, just they're leaking out. Were not intended for us. but we would still be able to pick it up. And in principle, we could detect sort of airport radar-like thing for other stars within 60 parsecs using these two telescopes. And if we revisit this plot that Leo made, we can see that SKA covers this purple range and NGVLA this blue range. So the other thing that we can see now is that they both will give us some region of the spectrum that have never been searched by SETI. So that is also possibly ways to find things that we haven't found yet. Summary. Okay, what we talked about. And interferometric SETI has the advantage of a larger field of view. So more sky mapping speed, hopefully find more, study more stars. With MeerKAT and the VLA, the goal is to observe 1 million stars within the next 2 years. And this will provide key knowledge for the search using SK and NGVLA. And the comment here is that the SETI community really welcomes collaboration and commensal observations. So if you have something that you think we can do together, do get in touch. Thank you. That's all I have.
Thank you so much, Sherry. This was interesting enough to make me consider moving my field. So I really like this. I'm the host for Sherry, so I'm the one who will lead the questions here. So let me see. Do we have any questions from the audience? Yes.
I have a question about the graph with sky coverage. Maybe it's one back.
Yeah.
Here, like sky coverage, we use like octans, right? Like 8/8 is like full coverage means full coverage, but I didn't understand the unit here, like degree square, like what does that mean?
Yeah, so that is kind of the angular size. If you ask, so for example, that one whole sphere would have something like 40,000 square degrees. Well, it's kind of like the projected area. If you have 1 degree times 1 degree, like it makes an angle.
Oh, okay, thank
Mm-hmm.
So you talk about these different beams that you can form.
Yeah.
I was wondering how do you define those? Like you mentioned like 65
Yeah.
for MeerKAT, I think. So how are those defined? Can you change the number? Like how does it work?
Yeah, so basically it depends how much GPU resources you have. Like more, if you have infinite amount of computing resources, you could in principle farm a lot of beams. So okay, some of them will have redundant information, but it's yeah. So for MeerKAT, we have enough computers to farm the so-called 64 beams, so that 64 different line of sights, and so we could choose where to point them to. We could farm less, but we could not farm more under this current setup.
Sorry. So those beams, what are they functional? Just the GPU or just the number of antennas?
What are they limited by? Well, mostly the computing resources that you have. And possibly, yeah, like the GPU power, like how much, okay, well, the thing is we need to run it real time because we want to piggyback on all the observations. So things are going on, like we are not saving the data and dealing with it later. So you gotta have enough GPU to form these beams, which is some kind of correlation in a way. You have to do all this correlation in real time and as also you have to do your SETI search beamforming just one step, right? So there's a lot to be handled by the GPU cluster. You need to have enough computing power to keep in real time, and you also have to have enough bandwidth to make the data flow. So this is what limits the number of beams. Yeah.
Sorry for jumping like that, but I had a similar question also, because the graph that you showed, basically you have, I don't know if you are pointing all the MeerKAT antennas in one direction, or you just, I'm a bit confused about that. So you point all the antennas to form one beam, right?
Yeah. In fact, so well, okay, it depends on what the primary observer chosen, because here what we are what we are selling is the commensal observation. Basically, we don't control the telescope. Someone else is doing something. We're just copying the data. And usually, so it depends on what the primary observer asks for. They can ask for different things, but let's assume that the primary observer asks to have all the antennas point at one position. This is most likely the case. And what I'm saying is that even if you have all the antennas pointing to the same direction, in fact, you can still see a lot. It's not a single pixel. It sees enough skies that we have other stars in the background. But the data have, like all the 64 antenna were pointing all to the same direction, and the data are all collected, yeah, in order to form the beams.
Anton, you have any question?
Yeah, since I assume that most of the observations will be commensal.
Yeah, I think so.
Yeah, but then which are the requirements in terms of frequency resolution, time resolution you will require for the normal observing mode of these two interferometers for MeerKAT and.
Yeah, I understand. Yeah, so I think commensal it's a good way to go. It gives us so much more sky. So yes, indeed. But then we are a little bit under the mercy of the primary observer, whatever they choose. We think for SETI, we really need Hertz with Hertz frequency resolution, and nobody does that, because as I said, this is how we're trying to differentiate, because astrophysical signal is just not so narrow. So nobody does that. I don't think right now we have a concrete plan of exactly how we can do this. I mean, for the MeerKAT and for the VLA, we provided our own cluster that copy the data from a more upstream stage. It's kind of the raw voltages, so that we can form we can do the very fine frequency resolution. So I'm not sure if we can do that for the SKA yet. The discussion just hasn't happened at this level. But I think at the same time we have to be open-minded. Like maybe with the machine learning algorithm, we could try to use whichever data type that we receive and see if we could detect something using that.
I understand that you're looking for technological signatures by studying just one channel, but have you considered the transmission of information in a multi-channel?
Yeah, there are really a lot of possibilities here. There are certainly people who talk about those. There are people who talk about broadband things too, because it could also be that way. Yeah, I think here we just decided, okay, let's try one thing first.
Yeah, you mentioned before that the standard for this SETI work was actually the archival telescope. Even though you presented a table that really convinces that the interferometers are way better, but I'm sure that there is some advantage, right, of using single-dish telescopes. I mean, you mentioned the GBT and the VLASS telescope. So yeah, I would like to know if these interferometers are way better, than what are the advantages of using single-dish? And then if there is some convincing advantage, then have you considered not necessarily you, but the community moving towards, for example, the 500 telescope?
Oh, yeah, okay, I see. Okay, multiple parts here. Now, the archival thing. I think I didn't explain it well. So, okay, there were also SETI search done with archival, but when we use this archival for the standard, it's not for searching. In fact, archival, once upon a time, had this planetary radar. It was an emitter. It sends radar. And so and it was the most powerful radar on Earth. So we were saying, okay, if the aliens were sending radars as strong as the archival can send it, then we can detect it or not. So this is the archival standard. But anyways, there were also SETI project on archival, and there are also SETI project on FAST in China. In fact, we try to get our hands on as many telescopes as possible. I mean, I think interferometers are good because it gives us the mapping speed, but single dish definitely have advantages as well. I mean, it's bigger dish and it's very good at pointing to one thing. And for example, I think there would be a use case. It's like when MeerKAT or VLA would detect something, we could then use Parks and GPT to confirm it. Look at this position and see if you can detect, right?
Okay, one question from Javier. There's a lot of interest here.
Maybe it was in your figure at the end, the figure of merit, but are you not using chimes to search also for signal because you have already the data, high resolution?
Yeah, chime would have been great too. Because chime is also very commensal in its design. It doesn't have the Ethernet multicasting, but it does make 3 copies of the data. So I'm doing a bit of side promotion because I'm from Chime, so I can talk about them. So Chime makes 3 copies of data. One goes for cosmology, one for pulsar, one for FRB. So it's really parallel in this way. One could add a SETI one and just add a SETI at the same time. And we talked about it, but the problem is there is not enough people. And so, I mean, I think Breakthrough Listen in principle could financially support it, but there is not enough people to work on it. So it didn't continue.
How would our signals from Earth, how they would be seen from outside? It would be just hundreds or thousands of very small, I mean, narrow signals randomly going up and down, or how would the signal from Earth be seen outside?
Yeah, interesting question. So I sometimes say that the search for SETI is like detecting RFI from space. Are you all radio astronomer? I'm not sure, but any radio astronomer knows about RFI and hated them because it just like contaminates our data. But SETI, it's kind of like trying to detect RFI from space. Now you're asking what our signal would look like from space. So I'm guessing it would look like our radio data full of our own RFI, but just maybe a bit weaker.
Okay. Are there any online questions?
Please.
Oh, sorry, I didn't see you in the last time. Go ahead.
I am still a bit confused about these beams. The smallest one is the primary beam of the telescope, or rather the synthesized beam?
Yes.
Because I'm confused about the size.
Yeah, the green is the primary.
Sorry?
The green one that represents the green is the primary, and usually so maybe I can explain it this way. There are, for example, in the case of MeerKAT, there are 64 antennas. They are kind of small, so each one sees each one has a large primary beam. That's the green, and once you combine all the 64 data streams together, you can make synthesized beam within the green that are much more fine, and those are the red or blue.
And then are you obtaining images or just the total power, let's say?
We are just doing beam forming, so not images, but there are some people who are starting to think about doing imaging, searching in the imaging field, but it's not so developed, let's say.
Because for example, in Proxima Centauri, you should be able to locate the position where the mission comes from. It comes from a radius close to the star or a larger orbital radius, for example.
I think the thing with, the main problem with imaging is the high data rates. So we have, the whole plane, and okay, maybe we just want to see the one star. I guess beamforming, it's, I don't know, on the first sight more efficient that way. But yeah, some people are thinking about imaging.
And also another question, you are discarding the millimeter range.
the star.
So you are only considering the centimeter
Yeah,
wavelength range, for example, because from the ALMA archive, in principle, you could obtain some data for the atmosphere, the potential atmosphere. The planets will be make the signal lower, but in principle, there is a lot of data there.
yes. I'm not aware of anyone using ALMA, but really in SETI, the main problem is not enough people. Well, I guess this is a problem for everyone, but we just don't have enough people to work on this field. So I didn't manage all the facilities. There's many other radio telescopes, but there are also some optical ones. But in ALMA, I don't think so. If you have some students.
Okay, so clearly there is lots of questions, which shows there is interest. So I kind of wanted to finish, and if you have more questions, feel free to come and visit, and we also have a lunch meeting after. But I wanted to finish with a question that I know you answered in Marcus's interview yesterday. The view on SETI has been kind of interest, looked down upon, no funding. And how do you feel the view from your colleagues from the astronomical community is on it right now?
I think it really has changed a lot. In the last 10 years or so, the SETI community grows so much, a lot thanks to private donations. There were some individuals that have the financial means, and they are so interested in this topic, and fortunately they supported a lot of research, and there are a lot of new people, young people, who joined SETI, is doing the PhD on this topic, and it funded these major programs on the best telescopes around the world. And I think everything, it's really positive. It is, I mean, in the past it was kind of ad hoc, like some people did a little project here and there. Now we are really starting to coordinate effort, like we scan the sky properly, we analyze it with some standard software that are well published, and on GitHub, people can actually check it. So I think this is a young field that is developing. It's going in the right direction.
Sounds good. Okay. Well, let's thank Jerry again. And I'd like to remind those that are coming to the lunch meeting at 2 o'clock that it's in the C building, and there may be extra spots if anyone else is interested in coming listen. That will be more towards the SPA Cradle of Light and the research that is being done right at the end. Okay.